Okay. Well, good morning, everybody, and welcome. It's Friday, so yay. That's always good. We're still working on Chapter 10, this vibrational motion, so simple harmonic motion. I'm going to continue talking about that. And then it kind of is going to lead us into waves, just some similar equations. Got Yen here in second row, who's keeping an eye on the ed discussion board and the class's topic in particular. Anything yet? Not yet? Okay. So she's got the wireless mic, but any of you can feel free to interrupt me at any time. I still need a couple volunteers for the December 7th, December 8th, which is Thursday, by the way. We're going to be in here on a Thursday at 11 because that's my Make Up Monday class, if that's all right, finishing up Chapter 11. So there's course evaluations. So this morning, you should have gotten an email from course evaluations at utoronto.ca inviting you to evaluate this course and all your courses on Quarkus. It takes about 10 minutes to answer the questions and enter your typed in thoughts about how things went for you this semester. Your answers and thoughts are anonymous, but are very important to me and Roya. And we don't get to read them right away. Sometime in January, after the course marks are all in, they send us a link, and then we can read all of your comments, look at all of how you evaluated us, and think about how we taught this course and how we want to teach it again in the future if we do again. So it's also a really important part of promotion through the ranks and how people like us are promoted and rehired and things like that is how the course evaluations go. So you have a lot of power by filling out these course evaluations, and I really appreciate it. Promise I'll read them. I also, as extra kind of encouragement, am going to give what's called a, fractional, like course evaluations fractional bonus point. So it's not a point, it's something between 0 and 1 that will be added to your final mark in the course, depending on the response rate to these course evaluations, which I can monitor. So course evaluations, you don't have to do them now, they're open until December 9th, but basically every time any one of you does your course evaluations, you just add 1/765th of a percentage point to every student's mark in the whole course. And so if all of you do it, then you all get a +1. If none of you do it, nobody gets the bonus, and that's fine too. But make sense? Yep. You didn't get an email. It says it's open. I heard a yeah, we did. So it's on Quarkus as well. You can click on course evaluations over on the left. There's a whole link called Coursey Vowels, and then click on students for that. But that's weird if you didn't get the email yet. It was supposed to have gone out this morning, quite early. This is just a little reminder about the final exam, which is Thursday, December the 15th, from 2 to 5 p.m. And when they say 2, they mean 2 on the dot. They don't mean 2:10. And that is true for all of the final exams at U of T. They start on the clock. They don't start at U of T time. So, so it's a whole course. So chapters like 1 through 11, 20 multiple choice problems, and 2 written answers. So it's really exactly twice the length of a term test, but you get a little more than twice the time. You'll have 180 minutes, I guess, to work on it. So I don't think it's going to be a rush for you. Also, I think since it's the whole course, I would like to allow 2 aid sheets, meaning you also get a calculator, which is allowed to be a programmable calculator, but not a communicating calculator. So you're not allowed phones or smartwatches, but you're allowed any kind of calculator you want. And up to 2 8.5 by 11 aid sheets that you're allowed to write on both sides. So that'll be specified in the aids. And like I say, it's not run by me, it's run by these exam invigilators. So you can be extra careful to obey all the rules in these things. I've seen students, like they continue writing a little bit after or something like that, and one of these exam invigilators, they'll throw the book right at you, and you end up like in the Office of Student Academic Integrity, months and months later with your marks suspended and all this stuff like that. So they really don't mess around. They're like cops, and you can't mess with them. And I'm just there to like answer physics questions, so I can try to advocate for you, but they have more authority than me. So, and sometimes they're not the nicest people you're ever gonna meet. So like don't have your phone in your pocket. That's the main thing. They will. If you get caught with a phone in your pocket, you're in a huge amount of trouble. So. Also, you need to know where your room is. So this is your last name on the left and the room code. And there's all these building codes, and it's all the heck over campus. So, like, what's ZZ Vlad? Well, it turns out to be the St. Vladimir's Institute on the west side of Spadina, sort of near New College there. You have to be there. So hopefully you can figure this all out. And I promise I will make 1 or 2 appearances in the room. I'm going to be wandering around. I can only be at one place at a time, but I'm sending some TAs your way. They'll be there the whole time from this course. And like I say, I'll try to pop my head in to at least offer moral support or something. It's really up to you. I think you guys are going to be great. You're great students. You're going to do very well in this final. I think it's just keep doing what you're doing. This came in the ed discussion, and it sort of made me chuckle. There was all this, the student is like, it says 20 centimeter diameter, so should it be 0.1 instead of 0.2? If I am misunderstanding the concept, let me know. It's like, which is more likely? Either, you have had some sort of stroke and no longer realize the definition of radius versus diameter, or Professor Harlow has made a silly mistake on his slides. Like, it's got to be one or the other, right? So you just gotta trust. I did this in front of all of you on Wednesday, and not a single one of you shouted out, "Hey, you idiot, you're wrong!" Something like that to tell me that it's 0.1. So anyway, I updated my notes that I've posted. So sorry about that. It was an unintentional mistake. I guess there's the ed reader too. You could maybe it's their fault. I don't know. Somebody should have said something. Okay. What the heck are we doing? Okay, yeah, so it's this equation. I want you to stare at this equation for a little while. It's like there is that saying, an equation is worth 1,000 words. Do you know that saying? Okay. Anyway, in physics, you look at equations and you try to understand what they mean. What does it mean? What does this all mean to the world? So, in order to understand that, let's play a matching game. I don't know if this is going to work because I've never done a matching game on learning catalytics. I think for every one, you're going to get a pull-down menu, which allows you to choose if it's a variable, or if it's constant, or if it's a function. And maybe I'll give you a minute or so to look at this. I'm going to come and see what it looks like, because I can't see what it looks like from the student perspective on my learning catalytics. Let's put the timer on. Okay, weird. Yeah, you have to look at first choice, second choice, etc. You can figure out how many of these are constants and how many of them are variables from. Well, a variable would be like something that changes, I guess. It's listed above. So yeah. So first choice is the word function. Second choice is the word variable. I don't know. There's no difference between all the different choices. Yeah, I don't know if this is going to work. When I set it up, it told me I was allowed to have more than one of them be constants and more than one of them be variables. We'll see if it really does work. If not, I will just discount this question. Like, I hope it doesn't matter which constant word you choose.
Professor,
Yes?
someone asked where they could find the survey on Quarkus for the course evaluation.
That's a good question. I can try to call it up on this. Where is it? So one place I have been able to find it is I kind of go over to the left. There's something called Coursey Vowels on Quarkus. Click on that. And then for students, probably, it should show you, well, I don't know, or complete your evaluations, I guess. So over on the left, there's a little thing called Coursey Vowels. I have no active evaluations because I'm not a student, but you should have a bunch. You want to look at what's going on with learning catalytics? I'm not sure it's working. But anyway, thank you for clicking in. Basically, let me do it on the thing, and I'll leave this up for a little while. But what I'm looking for is that X is, it's actually the dependent variable, okay? And T is the independent variable. You guys know about those? Like T is kind of the thing that it just comes in on your stopwatch, and it's going tick, 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 tick. X is the thing you're trying to find. Where is the position of the object? So it's like the dependent on the time. And then A is a constant. It's the amplitude. Cos is a function. It's like a button you press on your calculator to choose one, to convert one number to another number. You press the cos button. Pi is a constant. It's 3.14. And T is a constant. It's the period. Okay? That's what I was going for here. I'm not sure the pull-down menus really worked, but thanks for your patience with that. It didn't do what I thought it was going to do. All right. Okay, so that's the idea. And why is this? Well, it's coming from Hooke's law, which is that force on a spring is negative k times x. What's the negative sign mean? It means that it's a restoring force. So if x is positive, the force is negative. It brings it back towards the origin. If x is negative, so it's to the left, then the force is positive, and it brings it again back towards the origin. So here's the position. If that's the position, then the acceleration is the force divided by the mass, negative k over x times x. So there's negative some constant times x. So what's kind of interesting here is that if you look at the x versus time and the a versus time, they're the exact same graph, but flipped upside down. And I guess with different units, right? And it's different by a factor of k over m. But it's worthwhile just trying to plot it. Want to do that? I think I'm going to use, I got different colors. Let's use blue for position. And we're going to release it from some A. So A here is like x max. Okay? This is what's called the amplitude. And then what will happen is that it'll get sucked towards the origin, and then it'll go all the way down to minus a. So this is 0. X equals 0 at the middle. And this is, we're applying here x versus time. And then it goes up through the origin, and then it's going to go back up to there, reach a maximum, and it'll kind of go down again. So, get it? That's supposed to be that's supposed to be cosine, as drawn by Harlow. So what we can do then in green often in this book, you can plot velocity versus time. And this is the slope, right? So the slope of the maximum is 0. So when it's at a maximum or when it's at a minimum, actually, the slope is 0. So at all these points where I'm putting green dots, I think the slope is 0. Then what happens is that the slope goes negative until it gets to a maximum negative value right at this time right here. So, and then it goes positive after here. This is positive slope, and it gets to a maximum positive value right here. So what does that look like? Well, you can kind of smoothly draw your line through these points if you can. Do you see what I'm trying to do here? This is maximum negative slope, etc. Okay, so this is, if you look at right here, this is V max, the maximum positive velocity it has, which is right when it actually goes through the origin, but from negative to positive. And this is negative V max. Same speed, but it's going in the opposite direction when it passes through the origin the other way. So every time it goes through the origin, it's reaching its maximum speed. And then sometimes we use orange to do acceleration versus time, and that's the slope of this. And lo and behold, the zeros are going to be where the maximum velocity, maximum or minimum velocity is reached. It starts off with a negative slope, then it reaches its maximum positive slope right here, then it goes through 0, and what do you know? Look how the orange line is kind of just the flipped upside down of the blue line, just like we thought, because the force is negative some number times the position from Hooke's law. So it makes sense that the acceleration is negative some number times the position. So this is the beauty of the cosine curve and how it ends up solving this. This is A max, and down here is negative A max. So if you don't mind trying to sketch this, I think it's sort of instructive. I can't draw that X there. To try to draw these slopes. It's a nice calculus thing too. If you know how to take the derivative of cosine, I think it's negative sine. And if you take the derivative of sine, it's positive cos. So you end up with the derivative of a derivative, and you get a negative cos at the end. That's how they do it when they do the trial solution in calculus class. Okay, next thing. This is important, and it's one of these equations I need you to kind of stare at. Do you remember we had all these constants? There were two constants in this equation that you don't know. One of them is the one is the amplitude, A, capital A, and one of them is the period, capital T. There's also a lowercase t, which is a variable. So, the period, capital T, is set by the properties of the system. So it doesn't matter what you do and how hard you kick it or where you release it from, it's always going to have the same period if it's the same like spring and same mass. Because the period is 2 pi times the square root of m over k. And the other constant, A, is set by the initial conditions, such as basically how far away from the origin you release it from rest, that's A. Or, I suppose there's another way of setting up simple harmonic motion is you could start it from equilibrium and just give it some initial velocity. That would also work. Okay, let's stop the other one. It's the matching. I don't think that matching worked very well, to tell you the truth. Let's do a regular multiple choice question. So remember, the variables here, I'll list them here. The question is, which of the two constants capital A and capital T, in the description of simple harmonic motion is determined by the initial position and velocity of the mass. Remember let me just say here, the independent variable is T. Oh. This is kind of like if you were listening to what I just said. So this is, give me another 30 seconds, and I'll tell you the answer. I have 195 responses. There's got to be more of you in here. Hi, balcony people. Are you coming or going? You're going. See you later. Have a good day. Okay. 5 seconds. 4, 3, 2, 1. And I almost stopped the session again. Let's do it after delivery. Survey says 63% of you are saying only the amplitude is set by the initial position and velocity of the mass. That is because T is equal to 2 pi times the square root of lowercase m divided by lowercase k. These are properties of the system. It's the mass of the mass and the spring constant of the spring. Once these two are set, you have the period. It doesn't matter what amplitude you release it from, the period's always the same for simple harmonic motion. But the amplitude changes depending on whatever the initial velocity and position are, okay, of the mass. Okay. So this is just, again, a reminder. So the other thing I wanted to do really quick is just make a comparison. This book does this, of uniform circular motion and simple harmonic motion. So imagine you've got something going in a circular path, and you set up your y-axis and your x-axis, for example. And here's your object, and it's going around in a counterclockwise, for example. So if you could describe its position, I guess, by an angle, theta, from the x-axis. And you could say the radius here equals r. I'm going to say the radius equals a, just for fun. And you have an object here which moves with constant angular velocity. Omega, got to try that a little better. Omega in radians per second. Okay, so theta final is equal to theta initial plus omega times t. We can set theta initial equals 0, and so theta is equal to omega times t. And omega is equal to 2 pi divided by the period. So you can plug that in, and you can see that omega is equal to 2 pi over t, capital T, times lowercase t. The other thing we can do is look at a little triangle. If we want to figure out x, and there's y, and here's theta, and here's a, the radius, then I would say that cosine of theta is equal to x over a. So we can say that x is equal to a cos theta. So basically x is equal to a times the cosine of 2 pi over capital T times t. Does that look at all familiar to you? I'm just looking at the x position of uniform circular motion. There's also a y position, which I didn't put there. And then simple harmonic motion, which is a mass on a spring. There's no circular motion here. What I'm just doing is I'm saying here's x, and it's going back and forth only in the x direction. And here's x equals 0. I'm going to say a sub x is equal to negative k over m times x. I'm just going to say 2 pi over capital T is equal to the square root of k over m. So a sub x is equal to negative 4 pi squared over capital T times x. And we have this trial solution. Here, I'm sorry about the messiness. Let me draw that again. In the brackets there is, I think it's 4 pi squared divided by capital T. So the trial solution here is that x is equal to a times cosine of 2 pi over capital T times t. And, mathematically, simple harmonic motion is identical to one component of uniform circular motion. And to me, this is a very surprising result. I mean, when you have a mass in a spring, it's not moving in a circle at a uniform speed. It's just oscillating back and forth. And so, I guess it's a coincidence? I don't know. If anyone can explain why this works, I'd like to know the explanation. Yep. Yeah. Yeah, look at it from the side, yeah. Yeah. I agree. If you take a circular path and you look at it, it's something going in a uniform circular motion, you look at it from the side, it'll look like it's going back and forth. But I would argue there are many ways of going back and forth. I could write down probably 1,000 equations or draw it 1,000 different ways of how something could go back and forth. Why is it the exact same equation? Did you have a comment back here, orange shirt? I think that's right. K over m. Yeah, t squared. Thank you. Perfect. All right. I appreciate that. Let me get these notes right. Otherwise, I have to correct them later. So that saves some time. Okay, let's do another one. Wait, almost. What are Vmax and Amax? If the position function is that, then here are the velocities. So yeah, there's the t squared again. So that's good. You square the 2 pi over t, and you get a 4 pi squared over t squared. So that's absolutely correct. So basically, x max is equal to a. Why is that? Because this whole thing, cosine, remember, cosine goes between -1 and +1. So that's something to keep in mind. If you type cosine in your calculator, you never get a number greater than 1 or less than -1. It's always in the middle somewhere. So if you're doing a cosine of something, blah, 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 and multiplying it times the amplitude, that means that x is always between -a and +a. Similarly, sine is between -1 and +1, so that means that V max is equal to this thing. Well, actually, let's just call it the positive of this thing, 2 pi a over capital T. Because sine only goes between +1 and -1. So whatever is in this thing can never be greater than or less than, greater than 1 or less than -1. So this has to be that. And then A max, again, here's a thing that's 1 at the most, is going to be, you can either call it this, 2 pi over capital T all squared times A, or you can say it's equal to 4 pi squared A divided by T squared. Either one. Where, so A is the amplitude of the vibration, and T is that period of the vibration. So these are handy things to have on your aid sheet, I think. What's the maximum velocity of some simple harmonic motion? It's always 2 pi A over the period. Or what's the maximum acceleration? It's always this 4 pi squared A over period squared.
Professor?
Yep.
Someone said if amplitude is set by the initial conditions, including initial position and initial velocity, how does the initial velocity influence the amplitude?
Well, if the initial velocity, it sort of depends on both, right? If the initial position is at the origin, which it sometimes is, and then the initial velocity will just give the will give the amplitude, I guess. The more the speed, the more the initial speed, the higher the amplitude. You know what? We're going to talk about this. That's a really good question, but we'll talk about it a little more when we talk about the energy of simple harmonic motion, which is coming up. But let's do learning catalytics. This one is about what's called the BMMD, the Body Mass Measurement Device on the International Space Station. So there's no, you don't feel the force of gravity when you're in space because you're in free fall, you're orbiting the Earth. So if you stand on a scale, there will be no normal force on you and you can't measure your mass. And astronauts, first of all, are very driven people who really like to take care of their health. And second of all, they have a real reason to worry because when you're in a weightless environment, your muscles begin to atrophy. So they need to do a lot of exercise and they need to really measure their body mass pretty frequently to make sure that they're staying healthy up there, especially when you're up there for months. So there's a device, which is like a pogo stick. They attach themselves to it. She lifts up her feet, so she's not touching anything, and then it just oscillates her back and forth. And it measures the period of oscillation. So, and if she gets off of it, the period of the pogo stick alone is 1.2 seconds. If she then grabs onto it, and it's the same spring constant, then what's going to happen to the period? Compare with your neighbor. Check your neighbor, please.
Professor, there's another question.
Yes.
For comparing uniform circular motion and simple harmonic motion, are they similar? Because if we draw the graph, both of them shows a period function.
Yeah. Again, I do get it that if you look at uniform circular motion on the side, it's periodic. It goes back and forth. What I'm a little surprised by is that the equations are identical. You know, cosine, what the heck is that? That's from a SOHCAHTOA, it's from a triangle. So why is there a triangle when there's a mass and a spring? There's nothing moving in a triangle or a circle. It's just a mass going back and forth in a string. So where the heck does the cosine come from? Yeah, it's the solution to the that's what my math professor said. He said, it was really, I completely remember this moment exactly. I had a calculus professor, and they got to the second order differential equation. And then it was like he stopped, and then he turned around, and he said, we will now introduce the trial solution. And then he went back and he wrote cosine, and then he solved it all out, and everything worked out. But I raised my hand, I said, wait. Where did you get the cosine from? And he said, that is the trial solution. I said, yeah, but why cosine? He said, look at that. He referred me to the rest after and showed how it works so beautifully. And I was like, yeah, but right here, where does it come from? Like, it was divine inspiration. A cosine just plops down in there, and it all works out. I mean, yeah, it works. Your complex exponentials, yeah. True. Yeah. All right. Well, if we're going to get on to we're going to have to talk about, we'll bring this after class if we're going to get to complex exponentials. Going once, going twice. I'm not kidding you. I am a little mystified by the whole thing. Anyway, it's the magic of physics. 76% of you are arguing that it should be more than 1.2 seconds. This is what I like because basically it's just that equation, right? Which was that t is equal to 2 pi times the square root of m over k. K does not change. K is the same. Oh, thank you, Pius. Saving my ass there. But mass is bigger. So that's going to increase the period. Appreciate it. Okay. Not going to do that. Maybe do it next time. Getting a little behind. I want to get through, talk a little bit about energy of vibrational systems. Because somebody was asking about this speed, and I think it's a great question. Okay, so what we're talking about a cart on a frictionless surface, going back and forth due to a spring attached to it. It goes to a maximum of plus A, minimum of minus A, and just bounces back and forth. So, let's start at 0. At 0, its displacement is plus A, and we release it from rest, so its kinetic energy is 0. But there's an elastic potential energy of 1/2 Ka squared. So we're just thinking about the energy. Then, look, what is going on in this thing? A quarter of a period, so let's go to this thing. I don't know how I've organized these things. A quarter of a period, it goes through 0. So now, the spring no longer has potential energy, but it's moving at some speed V max. So the energy is now 1/2 m V max squared. That's all kinetic energy. So when we compare, let's just look at 0. Sorry, there's a 2 there. Versus a quarter t. What I think has happened is that at 0, all the energy is potential, energy stored in the spring, and the mass is not moving. But when it goes through equilibrium, it's moving as fast as it can possibly move, but there's no more energy in the spring. So I would say that it's kind of sloshed over. All this energy has been converted to kinetic energy. And that's exactly the idea here, is that the energy sloshes back and forth. The total mechanical energy E is a constant. But it can be stored either as the blue curve, the potential energy in the spring, or the green curve, the kinetic energy, but it's actually the sum. So this is it. E is equal to 1/2 mv squared plus 1/2 kx squared, but they always sum up to be the exact same number. So sort of like E is equal to k plus u sub s is equal to a constant. It's this amazing thing. It actually turns out that they're both, one's a cos squared and one's a sine squared. I don't know if you know this, but cos squared plus sine squared equals a constant. So potential energy, US, is equal to 1/2 kx squared, and kinetic energy, K, is equal to 1/2 mv squared. And, well, another way of looking at it, if you kind of plot it out, is the potential energy curve is blue, and then this difference here between the total energy and the potential energy is K, kinetic energy. Energy minus the potential. And this thing, U, is a parabola. US equals 1/2 kx squared. It's a parabola. Okay. Oh my God, 10 minutes. I want to do some more learning catalytics because I think it's good to try these things. So the equation, it's sort of weird. So we know that the potential energy when it's stopped is 1/2 Ka squared, and we know that the potential energy when it's moving, when it's at equilibrium is 1/2 mv squared when this is 0. So they equal each other. Or they equal, so the maximum equals A. So basically, you can rearrange these things and find that the maximum speed is equal to the square root of K over m times the maximum position. When the mass of the cart is large, it should move slowly. That's why m's on the bottom. If you've got a higher spring constant, the cart will move more rapidly. So, and don't forget, we've neglected friction. These would both, so friction and air resistance would do negative work in the system and gradually decrease its energy, eventually bringing the vibrating system to rest. But we're neglecting that kind of stuff. Okay, so let's do some learning catalytics. I'm going to give you guys 3 rapid-fire questions here. And I'll try to give you a hint. By what factor must we increase the amplitude of vibration of an object, A, I guess, at the end of a spring, in order to double its maximum speed during a vibration? So, do you remember, what the heck did we have here? Vmax, that's not the one I'm looking for. Didn't we have another Vmax somewhere? It was here. Vmax is 2 pi a over t. That's the one I think I might use. That's your reminder. Maybe a 30-second countdown.
There's another long question. It
Yes.
says, if velocity increases, wouldn't it complete more full cycles in the same amount of time than a smaller speed would?
That's a really great question. If the velocity increases, wouldn't it increase, have more oscillations per second? And actually, with circular motion, that would be true, right? If it was going faster. But it turns out not to be true in simple harmonic motion. If you're going faster, what happens is your amplitude also increases. So you have to go farther. And it ends up taking the same amount of time. Is it surprising result? Okay. So speeding up does not mean you complete more cycles per second. So let's, going once? Going twice? Excellent question, though. So hopefully just mathematically you see t is a constant here, okay? That's a property of simple harmonic motion. As long, and you know, there is, maybe it's not true if your spring no longer obeys Hooke's law or something, or your pendulum goes too high, but it's pretty close. Is that all? Good. So the one I like is basically 2. So t is fixed, doesn't depend on the speed. So you double the a, you double the maximum speed. Next question. By what factor must we increase the amplitude of vibration of an object at the end of a spring in order to double the total energy of the system? Total energy of the system. Right, so we had that somewhere, right? What the heck was it? Okay, it was, let me write it down here, the total energy of the system, total, equals, you have 2 equations for it. 1/2 mvx squared, V max, not Vx, because that changes, right? The maximum speed squared. Or E total equals 1/2 K times the maximum X, which happens to be A squared. So use one of these 2 equations to find the total energy. depending on which you're given. If you're told the maximum speed, you can use the top equation. If you're told the amplitude, you can use the bottom equation. All right. Maybe that'll be the last one we should do today. I way overplanned things. Okay. Go once. Go twice. And stop. Survey says. I'm seeing 90% of you like the square root one, which I think is right. So yeah, basically, if you increase A by square root 2, you'll double the total energy. It's even in italics. Okay, let me just get a little behind here, but that's okay. We have lots of time next week to catch up. Let me sum up. There's two things. We're going to talk about pendula on Monday, and we've already been talking about mass in a spring. It turns out there's actually a condition for this period what is equal to 2 pi square root of m over k, and that is that Hooke's law is obeyed. Hooke's law says that when you stretch a spring, there's a linear response of the force. But I think you probably know, if you've ever played with slinkies, that if you overstretch your slinky, it's no longer going to obey Hooke's law, probably, because you wreck your slinky after a while. And so you can overstretch a spring so that it no longer, or you can compress it so much that the coils collide with each other or something like that. So it's called small oscillations. For small oscillations, when your spring is behaving nicely, you get Hooke's law. And a similar thing for pendula. So how are we going to do it? Pius, ox plate? Nope. Screensaver? Yeah, that's what happened. Okay, so what I have here is, what do I have here? Two pendula that have the same length but different masses. This is 200 grams and this is 100 grams. And I displace them a little bit and they oscillate together. It's a little hard to see, so I'm in the way. Same frequency. And what's interesting too is that if I displace one a little bit and one a lot, they still oscillate together. Or maybe this left one I'll displace a little bit and this right one a lot. Or this up. Oh. People in the front row can see it. Out of batteries. Okay, fair enough. Let's go back to the laptop. But basically, the one that I'll be showing, we got plenty of time. The idea with the pendulum is that what matters here is the length of the pendulum, and this, G, is equal to 9.8 meters per second squared. So, in fact, the only thing that determines what the period of a pendulum is just the length of the pendulum. So if I had, and you're not really going to be able to see it, but maybe the video guy will be able to show it. This is a two pendula where the length of the one on the right is longer. And now you can see this frequency is higher, or this period is less, I guess, right? The period is smaller for the smaller length pendulum. Okay. So that's the only thing that determines this simple harmonic motion for a pendulum. So we'll continue on that. Here's another question. Maybe I'll even ask you this next time. So a child on a swing is a pendulum. And my question is, I guess, I don't know if you've ever stood up on the swing, but if you stand up on the swing, will the period be greater or less than? Or would it not change it? I'll ask that on Monday. Have a great weekend, everybody, and see you Monday morning. Thank you so much, Yen, for